Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to look at calculating magnitude and phase of a transfer function. And we'll do it in 3 steps. First we'll just review complex numbers, then look at magnitude and phase of a polynomial, and then finally go after the transfer function. So let's do a little complex number review. And we'll do this using a couple examples. So let's see, we have W1 is 3 plus 2j. We can plot that. Here's the real and imaginary axes. And let's see, 3 plus 2j is right about here. This is the magnitude of that complex number. And if I extend that line out, I can more clearly indicate its phase angle phi. So I can express this complex number right now in rectangular form, in polar form, as the following. The magnitude of W1, e to the j phi. Magnitude of W1 is equal to the square root of the real part squared plus the imaginary part squared, so that would be 3 squared plus 2 squared. That's the square root of 13. And phi is equal to the inverse tangent of the imaginary part over the real part, so that's 2/3. And that's about 33.7 degrees. And that's that angle right there. Great. Now, let's do another example. How about W2 equals -3 minus 2j? So we'll plot that again. Let's see, it's -3 in the real axis and -2j, so it's about right there. Here's the magnitude again. If I extend out a little dashed line, the phase angle is this angle, phi. So let's write it in polar form. Its magnitude is equal to the magnitude of W2, e to the j phi. Phi is equal to the inverse tangent of the imaginary part, -2, over the real part, -3. And the magnitude W2 is exactly the same as it was for W1. So let's see, magnitude W2 is equal to the square root of 13. Now it's tempting to get rid of those two negative signs and call it 2/3, but that would be completely wrong. So instead, let's break this up into pieces to calculate our phi. For example, we can say that phi is equal to this angle, which is 180, plus the inverse tangent, now let's do this little angle, of 2 over 3. Alright, so 2, that's this distance, over 3, this distance, opposite over adjacent. And add all that up and you get about 213.7 degrees. Very different phase angle, and clearly it looks about right from this picture right here. Great, so a little introduction, a little review of complex numbers. Now let's go after the polynomial in S problem. So for instance, let's say that we have some polynomial, d of s, that's of this form. S plus a1, s plus a2, these are all multiplied together, and then s plus a(n). Now what we're going to do is calculate the magnitude and phase of this stinker at a particular value of s. We'll call it s0, s0. So the magnitude of d at s0 is equal to the magnitude of that complex number s0 plus the complex number a1. And then we multiply it by s0 plus a2, dot dot dot, all multiplied together, s0 plus an. And the phase angle, and I'm using this notation with the little kind of a 45-degree angle to indicate a phase angle of d at evaluated at s0 is equal to the phase angle of s0 plus a1 plus s0 plus a2, that's a 2, plus dot dot dot, phase angle s0 plus an. That's it. So now let's do a little example. Let's say that we have a d of s that is s plus 2 and s plus 4. And let's evaluate its magnitude and phase at -1 plus 2j, some complex number. So d at -1 plus 2j, just replacing s with that value, is, let's see, I'd have a 1 plus 2j here. When I plug that in, the -1 and plus 2 gives me 1, then plus 2j, that looks good. And then if I plug this in, I'll get a 3 plus 2j. Great. So now the magnitude of d at this value of s0 is equal to the magnitude of this quantity. That would be 1 plus 4 times the magnitude of this, which would be 9 plus 4. Square root of 5 times square root of 13, and it's about 8.1 or so. The phase angle of d at s0 is now, I'm going to key off of these two quantities, it'd be the inverse tangent of 2 over 1 for this term, plus the inverse tangent of 2 over 3 for this term. And that gives about 97.1 degrees. Okay, so now we know how to take the magnitude and phase of a polynomial, and the last thing to do is to find the magnitude and phase of a transfer function. I'll abbreviate it like that, XFR for transfer and FN for function. So let's say we have some transfer function that has a numerator, n of s, and a denominator, d of s. Well, the magnitude of g is equal to the magnitude of n divided by the magnitude of d. And the phase angle of g is equal to the phase of n minus the phase of d. And that's it. Now, we're going to explore this using two different ways. First, we'll just use straight up math. And the second way, we'll use a graphical technique. And they both have benefits. So let's do this via an example. We'll say that S0 is -2 plus 4j. So that's the point at which we want to calculate the magnitude and phase of g. And our g is 7s plus 4 over s squared plus 4s plus 8. So let's do it the math way first. So I'm just going to say that the transfer function g evaluated at s0 of -2 plus 4j is, and I'll just go ahead and plug all this in. So let's see, here we get a 2 plus 4j in the numerator, and in the denominator we'll get a -2 plus 4j for this term, and then we have to square -2 plus 4j, so we get 4 minus 16j minus 16. Then we have this term, 4s. So let's see, that gives us a -8 plus 16j. And then we have this, plus 8. All kinds of wonderful simplification occurs here. Let's rewrite the numerator. And in the denominator we get, let's see, a -2 plus 4j. And from here, a -12. Now, let's see. I'm going to slide this down just a little bit so we can keep going. Now, let's go after the magnitude of g first. So the magnitude of the numerator, well, the magnitude of 7 is just 7. The magnitude of this other piece is 4 plus 16 square root, divided by the magnitude of this piece, which is another 4 plus 16. Times 12, the magnitude of -12. Those two cancel out and we get 7/12. Great. Now let's go ahead and do the phase of g. So the phase of g, we have to be a little bit thoughtful here. We're working with this transfer function. What I'm going to do is I'm going to treat each one of these terms all four of these terms as if they're complex numbers. So if I look at 7, if I were to sketch a little picture of what 7 looks like in the complex plane, it's sitting somewhere over here, and its phase angle is 0. So I'll just give that as 0. Plus the phase angle of this piece right here, which would be the inverse tangent of 4 over 2. And so far, so good. Minus, well, now let's do the phase angle of negative 12. Well, negative 12 is sitting over here. And so its phase angle is actually 180 degrees. And now I have to get the phase angle of this piece. Well, let's draw another little picture of that just so we know what we're doing. We're going to get the phase angle of negative 2, so over here, plus 4j, boop, 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 up here somewhere. That phase angle, phi, is equal to 90 degrees. That's this piece of it, right to here, plus the inverse tangent of 2 over 4. 2 over 4. There it is. And if we go through all the math here, we'll get negative 233.1 degrees. Boom. There it is, straight math. Just remembering that the magnitude is the magnitude of the numerator divided by magnitude of the denominator, and the phase angle is the phase of the numerator minus the phase of the denominator. And the only tricky part is if you have some negative constants floating around, you just have to make sure that you accommodate their contribution of phase. But now let's do, actually I'm going to go to a clean sheet and let's do the graphical technique. This is kind of fun. The way it works is this. Let me rewrite the transfer function. It was g equals 7s plus 4 over s squared plus 4s plus 8. And this thing actually has complex roots at negative 2 plus minus 2j, and that'll become important in just a second. So the way that this works is you plot the poles and zeros in the complex plane. So let's see, I'm going to go 1, 2, 3, 4, 5, 1, 2, 3, 2, 3. And let's see, I have a 0 at negative 4. So I'll put a little O right there. I have a pole there at the origin from there. And I have a couple poles at negative 2 plus minus 2j. So there and there. And the complex number that we're working with is negative 2 plus 4j. So now what you do is you put a dot at negative 2 plus 4j, which would be right about here. You draw arrows from each of the poles and zeros up to that point. So I have one there, I have one here, one there, and one there. And what I'm going to do is I'm going to actually give these a name. I'm going to call that phi p1 for the phase of pole 1. And this one is, let's call it phi p2. And it gets a little messy, but let's call this angle phi p3. And this angle phi z1, because that has to do with a 0. Now, the magnitude of g is just equal to the magnitude of each of these arrows, of all of those arrows. Now I also have to take into consideration this scalar, this constant that the whole transfer function is multiplied by. So the magnitude of this would just be 7 times, I'll do this magnitude first for the arrow associated with phi z1. It would be the square root of, let's see, 2 squared plus 4 squared. Oops, 4 squared. And then in the denominator, I have all the other magnitudes of all the other arrows. So this one, and this one. So let's see. I'll have, let's see, this distance is just 2. So that's this one right here. This distance is 6. Those are easy. And then this distance, that magnitude, is equal to the square root of 2 squared plus 4 squared. These cancel, and again I get the 7/12 like we had before. Now the phase angle of G is equal to the phase of all these 0 pieces minus the sum of all the pole pieces. So it would look like this. And let's go ahead and do that. Let's see. The phase associated with Z1 is the inverse tangent of 4/2, if I look at this angle right here. Minus phi P1 would be 90. That's this piece of it. Plus the inverse tangent of 2/4. That's this piece. And then we have the phase angle associated with those two arrows. And so I have 2 each at 90 degrees. That's phi P2 and phi P3. 90 plus 90. And you add all that up and you get negative 233.1. Exactly what we had before. So that's the end. That's how you get the magnitude and phase of a transfer function, either graphically or just by plugging in the complex number of interest, in this case, in this example, negative 2 plus 4j. So again, this is Gordon Parker from Michigan Tech, and thanks for watching.